Hello, my name is Paul Hepper. I am a senior research analyst here at the Southwest Research Institute. Together with my colleagues Brad Trantham and Chris Leval, we've created this overview for you of the UVS instrument, which is the ultraviolet spectrometer on the Juno spacecraft currently around Jupiter. And I'm going to give a brief look at the data processing regimen that we use both in space and here on the ground. And I want to start out by saying my apologies up front. I am going to be uncharacteristically using my notes over here. That's actually, I found out as I was timing this talk in the last couple of days that when I start extemporizing, that it runs long. So I'm doing this not so much to bury my nose and not have eye contact, but it's to keep from rambling. So, okay, we're going to be talking about Juno and Jupiter itself. Then I'm going to move on to UVS science. I'll be showing you some pretty pictures of the science we're getting back from the UVS instrument, and then finally on to the actual software itself. So Juno, it is a NASA JPL mission led by our own Scott Bolton as the PI. It was launched in 2011, arrived at Jupiter there in 2016. It's still on orbit. It is a 5-year mission planned to deorbit in about 3 years from now. Now, why go to Jupiter? Of course, it's an interesting place in general, but why this time in particular? Of course, it's the largest planet. It therefore has a big effect on all the rest of the solar system. Being the biggest, it was also likely the first to form. So studying it can tell us a lot more about Earth's own early history. Jupiter has a lot of other superlatives and interesting aspects. It has an intriguing atmosphere with centuries-old storms. It has the fastest rotation of any planet by 10 hours. It emits a lot more heat than it receives from the sun. It has 72 moons, including the largest in the solar system, which is Ganymede, et cetera, et cetera. But most important for us in this talk is that it has an immense magnetic field, some 20,000 times stronger than Earth's magnetic field. To give an idea of just how strong the magnetic field of Jupiter is, Fran Bagenal and Steve Bartlett of the University of Colorado claim that if Jupiter's magnetosphere were made visible, it would be the largest object in Earth's night sky. It would be fully 3 times larger than the apparent diameter of the full moon or the sun, and that's despite being 5 times, on average, further away from Earth than the sun is. So Jupiter's magnetosphere is ginormous. Let's go check it out. In fact, this is a striking image right here. Jupiter's magnetosphere is so elongated as well, so large, that the magnetotail stretches all the way to Saturn's orbit, which is a full 4 AU. To put it another way, if it was blowing the other way, then Jupiter's magnetotail would stretch all the way from Jupiter across the asteroid belt, across Mars' orbit, all the way to Earth. It's giant. But anyway, of course, Jupiter's magnetic field is not visible, but there are various ways we can sense it. One of the most readily at hand ways that we can sense Jupiter's magnetic field is by looking at the aurora. Here are some of the best images that we've had of Jupiter's aurora taken by the Hubble Space Telescope just a few months before Juno went into orbit. Very interesting stuff, and you can see in particular, let's use a pointer here. How about this one? Yeah, that right there is what they call the footprint of Io. Io is one of the main moons. All of the Galilean moons of Jupiter have a magnetic footprint on both the north and south pole of Jupiter. So there we are. These are the main objectives, science objectives of Juno, as you see. To number one, to learn more about Jupiter's origin and thereby more about the origin of the entire solar system. To better understand Jupiter's interior structure, what kind of a core it has, if any, et cetera, et cetera. to study its intriguing atmosphere down to a depth of 100 bars or so. That's a couple of 100 miles, 100 kilometers into the atmosphere. And then most relevant to us, to understand Jupiter's magnetosphere and its auroras. So that brings us to the UVS science. So, well, turns out that auroras glow very brightly in the ultraviolet, and Southwest Research is very good at making ultraviolet instruments. This indeed is the fourth in a series of similar instruments built by Sweary. The ultraviolet spectrometer is a shoebox-sized instrument, maybe about a boot box size. It consists of a folded path telescope. Here's my little animation. The light comes in and is broken up by the grating up there into its constituent ultraviolet frequencies, and then coded up in the electronics. Interestingly, the bulk of the electronics are actually kept in a second box elsewhere in the spacecraft inside of an inches thick titanium radiation vault, because Jupiter's radiation, because of that magnetosphere, is punishing. The UVS team is led by Randy Gladstone, and its mission goals are as so: to characterize Jupiter's aurorae, map the precipitating electron energies and any of the other particles that are accelerated by the fields, to observe the spacecraft footprint, and which you'll see a little bit more on some of the data I'm going to be showing, as it changes over the planet, and then to look for structure and variability in low latitude air glow as a tertiary goal. So, before I get into the software, let me show you some pretty pictures. Okay. This slide shows data taken in March 2017 from Jupiter's north magnetic pole, and there's a whole bunch of stuff going on here. On the left is ultraviolet amplitude. On the right is ultraviolet frequency. So it's the same image, just amplitude versus frequency over there. The instrument paints the image incrementally as the spacecraft moves and rotates twice every minute. Thus, you can see the painting going on. It takes about 40 spins or so to produce a full image at 0.6 Jovian radii. There you go. And so that's to say it takes about 20 minutes at an altitude of about 40,000 kilometers to produce this sort of an image. You can see many fun things here. You can see this dashed white line around both images. That shows the main auroral oval. You can see this fat yellow line growing along the side over here in the 8 o'clock position. That shows the sun position, sun direction. You see the X right here. That shows the nadir position of the spacecraft on the planet's surface. And then finally, which is most interesting to me, is that you see these dots. They're progressing down here. A little bit hard to see on there. And yellow over here, you have the dots that are progressing along the orbit line. They show the place on Jupiter where charged particles which are currently passing the spacecraft will impact Jupiter's atmosphere. So UVS can't sense those particles as they pass the spacecraft, but other instruments on the spacecraft do sense them. So they smell a sulfur ion whizzing by. They smell hydroxyl ion whizzing by, oxygen, whatever, and then we can tell, because it's just field lines, knowing that it will impact right down here, and we can thereby try to make a model as to what is going on to make all this otherwise intense activity going on down here. Some fun stuff is happening. We want to find out why. Okay, so here are 4 other images, similar sets of amplitude frequency images. I would like to have you notice 2 things about them. Number one is that the main auroral oval rotates between all these images. Here you see, I'm going to get this right yet. Okay. You see that here the low part of the oval is pointing here to the left. Here it's to down, to the right, and up. This actually corresponds to the low part of the image is at Jupiter dawn. Here it's at Jupiter noon, Jupiter evening or dusk, and Jupiter midnight. So that the oval itself rotates, which is an interesting thing by itself. But secondly, please notice that what's going on in the middle of the oval. Here we have a whole lot of activity. By contrast, here, not nearly so much. And it's most starkly shown right here on the day side of this very thing. You have a lot more activity than on the night side of the very same oval. This is a completely new and notable result that Juno has uncovered. Not only have we never seen such a good look at the dark side of Jupiter's aurora before, but the greater activity on the sunlit side is something that is completely opposite of what you would have on Earth. So these results, in fact, are so new that they have not yet been published. We're seeing them here for the first time. So here's an interesting one. This is the auroral curtain. It shows the very place on Jupiter's atmosphere right where the auroral oval impacts the upper atmosphere, and you can see that the high energy particles are exciting and making fluorescence about 1,000 kilometers higher into the atmosphere than the neighboring regions. You also see this black slash right here. That is an artifact caused by basically buffer overload on the spacecraft. Okay, here's our last image, or at least of the fun science stuff that I got to show you. The Juno spacecraft is constantly rotating at a nice leisurely 2 RPM. That means our UVS instrument has the opportunity to occasionally stare at the stars. We capitalize on this at least once every orbit by making use of the known brightnesses and spectra of the UV stars to calibrate our instrument. And one pleasant side effect of that is that we can paint pretty sky maps like so in the ultraviolet. So of course you can see the main galactic plane right there, and here's the large and small Magellanic Clouds. Here's the Great Nebula in Orion. There's the head of Scorpio, etc. So fun stuff. Okay, so now on to UVS ground software. Here is a block diagram of our ground data processing. We have data sources and data processes up there, okay. And our data processes are dominated by 2 main number crunchers that we have called Lima and Mike, okay. The data comes in from JPL by way of the Deep Space Network in 2 major chunks, the UVS Science and then UVS Housekeeping, totals about 100 meg per orbit of Jupiter. We add that to some operations plan files that are generated by our engineers here to identify what we're actually supposed to be looking at in a given image. All that gets pumped into the Lima process, which outputs a single file of about 1 gigabyte. Lima does mostly time correlation of all the data that comes in. So we make sure that everything has a stamp of some sort indicating what time it was actually taken. Next, we have spice kernels. Let me ask a question here, just out of curiosity, put you guys on the spot for a second. As a show of hands, how many people here have ever actually heard of or used spice kernels? Okay, good, thank you. That gives me an idea. I'll talk more about that here in a second, but yeah, SPICE basically is a space geometry system. It helps us know basically where we're pointing. So we load in these SPICE kernels here, and then along with the Lima product that came out of Lima right there, we pile that all into the Mike process, which does, well, in contrast to Lima, which did all the time correlation, Mike does all of the spatial coordination, identifying where we were pointing, et cetera, along with the help of the SPICE kernels. And since its data is a lot more digested, it cranks out stuff that's about 8 to 10 times larger than what Lima did. So Lima cranked out a 1 gigabyte file. Mike is about 10 gigabytes total. SPICE, as I mentioned, is a space science observation geometry system. It's maintained by NAIF, which is NASA's Ancillary and Information Facility, Navigational and Ancillary Information Facility, NAIF. It's a small office at JPL. Anybody here from NAIF? No, that'd be nice. Okay, it's used by a lot of different space missions, both U.S. and international. SPICE actually stands for something: spacecraft, planet, instrument, camera matrix events. Yeah, but nobody ever uses that. It's I had to dig around a while on the SPICE website in order to even find the acronym. Everybody just calls it SPICE. It is simply a way for identifying where things are pointing, what we're pointing at in space. In space, of course, everything is moving. The Earth is moving, it's spinning, Jupiter is moving and spinning, the spacecraft is spinning, stuff is whizzing around all over the place. How do we know that this little patch of otherwise indistinguishable cloud top is the exact same indistinguishable cloud top that we were looking at here a second ago? The way it is that we can use SPICE along with the time to determine exactly what we were looking at before. So that's what SPICE is. Okay, well, in the 2 years that that Juno has been in orbit up there, our data processing has evolved a little bit. The main changes are that we've added a number of elements of automation. We've wrapped several of these items in shell scripts. We've added some control programs, and in one case, an external database. Let's see, there we go, okay, like that. It used to be that, now it's more like that. The result is basically a modest speed up, but it is a substantial decrease in the amount of human hassle. So it is a big change for us. Okay, now we get down into the guts just for a little bit. The main function of our detector is to record ultraviolet photons as they come in. Specifically, we record the spectral, spatial, and amplitude aspects of every event. As this slide shows, we have two buffers. We call them ping-pong buffers. As one fills, the other one can be sent off back to Earth. So, of course, if the photons come in so fast that they fill up one buffer before the other one is done sending it back to Earth, well, then we get data loss, and that's exactly what happened in that previous image where we had that black slash across the image. And it's supposed to work like this. So, pardon the cheesy animation. So, it's interesting that it's supposed to be coming out in color. Apparently, it doesn't do that here. Yeah, sometimes that happens, but that precise one on that slash, I had to investigate. But it was probably from being blasted by too much radiation all at once. So okay, so we fill up the buffers, and as we fill up each one, of course, each packet then is dumped back to Earth, and periodically we insert a housekeeping packet into the stream. So as you see, the data stream here is occasionally has time data inserted right in along with the photon data. We call these time hacks. These are just the 18 least significant bits of the time string. Time hacks allow us to have a good temporal resolution without having to have the full cost of blasting down an entire time string that's in a housekeeping packet and wasting the bandwidth. So, but they do come with a complication, of course. Well, time hacks, these little guys up here that are right in the data stream, they only have the least significant part of the time. It'd be equivalent to you guys asking me what time is it, and I just said, gave you back the seconds. What time is it? 18, 5, 3. Yeah. That'd be fun until you hit me. But that's basically what it is. You can see, however, the advantage of that is that, and the downside as well. The advantage is that we can have a lot more bandwidth dedicated to science data. The downside is that every time hack has to be correlated to a full time string in one of the neighboring HK packets in order to make any sense at all. So, yeah. matching the 18-bit time hacks in data packets to the full 32-bit time strings in housekeeping packets is complicated. So in general, when data is coming down pretty smooth and simply, we generally have a data packet neighboring an HK packet all the way along. Sometimes data speeds up and we have to sort of stretch back. As long as we can see our way all the way back, we can say, okay, yes, this data works. But every once in a while, we get into a position where we have time gaps, missing data, packets that just didn't make it back, and we will not know, well, this data here, did it go with that housekeeping packet or this one? We have to throw that one out. So why use such a complex scheme? Well, overall, it does save bandwidth. It increases the science data throughput despite the occasional data loss. Anyway, that brings us to processing speed. As I had mentioned before, the Lima process up there, that one takes care of all the time correlations. All these correlations we just mentioned that go along with the time hacks, that is done by the Lima process right there. And thankfully, all the data in a single Jovian orbit, all 100 gigabytes we 100 megabytes we read in and 1 gigabyte we put out, we can crunch through in about 15 minutes. That's all good. By contrast, the exact same set of data coming out of Lima takes about 5 days to go through Mike. Mike, of course, has to do all the spatial processing, identify, understood. It has to do all of the spatial processing, all that stuff with the SPICE code. And what is up with that? Well, let's see if we can find out how we go to the next slide. Okay, all right. There we go. Yes, SPICE code is not, can't easily be run in parallel. That's unlike the Lima code, which automatically expands to engage as many cores as we will give it. It will run very quickly, digest all the data that we gave it. SPICE is not currently parallelizable. The NAIF team is working on it, and I certainly don't want to badmouth those guys. They have been a big help to us. In fact, the biggest reason why Mike runs so slowly is because we have to correlate every single photon, all millions of them that we get, using a SPICE call, every single one of them. So we're looking at different kinds of improvements, distributed computing over our own local network, our own local cloud. All that is very manual at the moment. And also, of course, automating Mike slowly. We're going to get there so that we don't have to intervene in the situation ourselves so much. And then that brings us to future directions. Advanced analytic methods are one avenue, like deep learning. Our intelligent systems division, in fact, you just heard a talk here about 2 talks ago, done by a colleague of mine. Our intelligent systems division has a lot of experience with image processing and high-dimensional data sets. And of course, there's insight discovery, as they are calling it now, where we'll just make use of some of the techniques of unsupervised learning to help the scientists ferret out hidden trends in the data. Those are things that we're looking at. So, well, there you go. That's kind of an abrupt ending, but there you are. I've shown you in this talk Jupiter and its amazing magnetic fields. I introduced you to the UVS instrument and shown you some of the pretty pictures and the science we're getting back. And I gave you a quick look at the way we process data. So I'll leave you with this image right here. This shows Jupiter's aurora and the Earth's southern lights. You can see Antarctica right there inside the circle. What's interesting to note about this is that these images are both to scale. Wow. So as with all other things Jupiter, its aurora could eat our planet. Okay. Thank you very much.
Thank you.
Mm-hmm.